In today's video, we are going to determine the new expression of the optical path difference when the source S is no longer on the perpendicular bisector of S1, S2. Note that the abscissa of S is XS here. The expression of the optical path difference is delta equals to SS2M minus SS1M. We have shown that we can write it as SS2 minus SS1 plus S2M minus S1M. This is AX over D. So what is SS2 minus SS1 equal to? Similar to S2M minus S1M, which was equal to AX over D, SS2 minus SS1 is also equal to AX over D. And which X? X of S. Then the analytic expression of the optical path difference will change. Look at the new expression of delta. We can ask a question here. Where do we find the central fringe now? Is the central fringe still at O? The central fringe signifies that the optical path difference at a point of it is 0. And as a result, AXS over D plus AX over D equals to 0. Now where is X? It is the abscissa of the center of the central fringe. We are going to denote the new position of the central fringe by O prime. We can simplify by A, and we obtain X of O prime is equal to minus D over D XS. Now look at this result. The abscissa of XS is positive. XS is in the positive direction. S is shifted upwards. D over D is always positive. XO prime is therefore negative. We notice that O prime is found here. This is the new position of the central fringe. Note that XO prime and XS always have opposite signs. If the abscissa of S is positive, the abscissa of the central fringe is negative. We can also add something here. The points S, I, and O prime are always collinear. When S is on the perpendicular bisector of S1, S2, the central fringe is at O. When S is shifted upwards, the central fringe shifts downwards. When S is shifted downwards, the central fringe shifts upwards. Now we are going to determine the expression of the optical path difference, where one of the slits is covered by a thin parallel-faced plate. What is a thin plate? It is a transparent medium, such as a very thin glass sheet, for example. Assume that E is the thickness of the plate and N is the index of refraction. Recall that the index of refraction of a transparent medium is N equals to C over V, where C is the speed of light in vacuum, which was found to be approximately 3 times 10 exponent 8 meters per second. V is the speed of light in the transparent medium of index N. V is always less than or equal to C. Thus N is always less than or equal to 1. The optical path difference is given by delta equals to S S2M minus S S1M. Note that this expression is valid in vacuum or air. But we have a problem here. This part of the optical path, which is S1M, passes through the thin plate, not only in air or vacuum. The problem can be solved by replacing this thin plate by another containing air, for example, or vacuum. That is to say, the optical path in the plate is equivalent to the optical path in air of a certain thickness. So how can we find this equivalent thickness? The duration of the passage of light in the plate is equal to the duration taken by light in air. This is a figure of the plate. Its thickness E. It has an index N. Light traverses the plate with a speed v. The duration taken by light from A to B is equal to tau, which is equal to the distance over the speed, which is equal to the thickness E over the speed v. But v is given by c over n. So tau becomes E over c over n, which is equal to ne over c. What is the thickness of an air medium that can replace this plate? Light will travel the air thickness in the same duration tau. The air thickness, for example, d prime, and the distance is equal to the speed multiplied by the duration. In air, this is c, so we get c times ne over c, which is ne. This is the thickness of air that replaces the plate. But since n is greater than or equal to 1, then d prime is greater than or equal to e. So the air that replaces the plate has a distance d prime equals to ne. Imagine removing the plate and replace it with a distance ne. That is to say, removing the distance AB and replace it by NE. Or adding to the distance AB a supplementary distance of NE minus E. Therefore, if we want to replace the plate by air, we have to add an additional distance to the path S1M. This additional distance is N minus 1 E. The additional distance is added to the path S1M. This additional distance is N minus 1 E. So SS2M minus SS1M plus N minus 1E. SS2M minus SS1M minus N plus 1E. This is equal to S2M minus S1M minus N minus 1E, which becomes AX over D minus N minus 1E. And this is the new expression of the optical path difference. When S is on the perpendicular bisector of S1, S2, and a parallel faced plate covers the slit S1. we can ask a very important question here. Will the central fringe remain at O, or will its position change? Always keep in mind that the central fringe is defined for delta equals to 0. The optical path difference is equal to 0. As a result, AX over D minus n minus 1 E is equal to 0. X is the abscissa of the central fringe, which is denoted as O prime. We obtain x of O prime equals to n minus 1 ED over A. This is the new position. N is greater than 1, so the new abscissa of the central fringe is at O prime, which is a point above O. When the plate covers S1, the central fringe shifts upwards to the same side as the plate. But if the plate covers S2, we notice that the central fringe shifts downwards. That is to say, the central fringe always shifts to the side where the plate is found. Now we are going to solve an application. Consider Young's setup, where S1 is covered by a thin parallel plate. The distance between the observation screen and the plane of the slits is 1.6 meters. The distance between the slits is 0.25 millimeters. The thickness of the plate covering S1 is E equals 5 micrometers, having an index of refraction 1.5. The radiation emitted by the source S has a wavelength lambda equals 0.625 micrometers. M is a point on the observation screen having an abscissa X. In the first question, calculate as a function of A, X, D, and E the optical path difference at M. The optical path difference is delta equals S S2M minus S S1M. Note that this is in air, but S S1M traverses the parallel plate, so we have to do a certain correction. We add to this n minus 1 E. Why? Since the presence of the parallel plate increases the optical path by n minus 1 E. The presence of the plate increases the optical path by n minus 1 E. So delta equals to SS2 plus S2M minus SS1 minus S1M minus n minus 1 E. But SS2 equals to SS1. We can eliminate them. We obtain S2M minus S1M minus n minus 1 E. But S2M minus S1M is always AX over D. The result is AX over D minus n minus 1 E. This is the optical path difference at point M. In part 2, determine the position of a point J where the central fringe is found. When we ask about the position, we mean that we have to find the abscissa. So how to find the abscissa of point J? Note that J is the position of the central fringe. and the central fringe is defined by an optical path difference of 0. Here's the optical path difference. We need to find the abscissa that corresponds to delta equals to 0, which is that of the center of the central fringe. Ax over d minus n minus 1 e equals to 0. X of point j, which is the center of the central fringe, and as a result, x of j equals to n minus 1 e d over a. This is equal to 1.5 minus 1 times 5 times 10 exponent minus 6 times 1.6 over 0.25 times 10 exponent minus 3. And the result is 16 times 10 exponent minus 3, or 16 millimeters. The central fringe in the absence of the plate is at O. In the presence of the plate, the central fringe is at the point J of abscissa 16 millimeters. This is J, which is found here above point O, since the parallel plate covers S1. Now for part 3. Specify the nature of the fringe at O. So what is this fringe that replaces the central fringe at O? At O, that is to say the point of abscissa 0. By replacing x with 0, delta becomes minus n minus 1 e, which is equal to minus 1.5 minus 1 times 5 times 10 exponent minus 6. The optical path difference at O becomes minus 2.5 times 10 exponent minus 6 meters. The question requires to specify the nature of the fringe at O. If delta is a multiple of lambda, the fringe at O is a bright fringe. And if delta is an odd multiple of half lambda, the fringe at O is a dark fringe. So we divide delta by lambda. We get minus 2.5 times 10 exponent minus 6 over 0.625 times 10 exponent minus 6. And the answer is minus 4. So delta equals minus 4 lambda, which is a multiple of lambda. Then O is the center of the bright fringe of order minus 4. Why? Since delta has the form of k lambda, where k is the order of the fringe, which is minus 4. So at O, we find a bright fringe of order minus 4, which is due to the presence of the plate of thickness 5 micrometers and index 1.5. And now for part 4. Determine the abscissa of the dark fringe of order 2. The dark fringe corresponds to an optical path difference delta equals to 2k plus 1 lambda over 2. The dark fringe of order 2 means that k equals to 2. So delta equals to 2 times 2 plus 1 times 0.625 times 10 exponent minus 6 over 2. The answer is 1.5 0.5625 times 10 exponent minus 6 meters. But this is the expression of delta. So delta equals to ax over d minus n minus 1 e. Delta equals to 0.25 times 10 exponent minus 3x over 1.6 minus 0.5 times 5 times 10 exponent minus 6. And the answer is found above. 1.5625 times 10 exponent minus 6. So after some calculation, x is equal to 0.026 meters or 26 millimeters. This is the abscissa of the dark fringe of order 2.